Okay, let's take a look at example 3 now. It says the table gives the values of the average life expectancy in years for a child born in the United States. Here's our table. Part A, the life expectancy in years of an individual born T years after 2004 can be modeled by the function L given here. Hey, catch this. It said T is the years after 2004. So I'm going to be specific. I'm going to put a T here. They didn't actually give me the T values. A lot of students mess this up. It's years after 2004. So how many years is 2004 after 2004? 0. How many years is 2008 after 2004? 4. 2012? 8. 2016? 12. 2020? And 2023? 19. There's our data that we're going to type in. Those are our T values. And T is in the place of what on this equation? Is T X or Y? T is your X. This would be our Y. Okay, we'll write 3 equations. We'll find A, B, and C and do all that, but I'm going to type in the calculator first. So I'm going to add a table. For the years, I'm going to do 0, 4, 8, 12, 16, and then 19. Now, I forgot to tell you all this. I'm going to go ahead and hit zoom fit on the scatter plot. What type of equation is this? Does it tell you? If you have a squared as your highest power, what is that? Quadratic. So I'm going to choose quadratic here. Quadratic regression. Okay, I did not tell you this. If you want to know how accurate it is, you look at the statistics where it says R squared. Anyone in statistics in here right now? Anybody taking statistics? Have y'all talked about this already? So in statistics, they usually use 2 numbers. They either say if it's better than 0.9, it's good. If it's better than 0.95, it's great. You see how this is 0.9861? That would be a very good model. Anything better, anything higher than 0.9 they consider good. Anything better than 0.95 is really good. Okay, that's a little statistics for you. So this is a good model. That's going to be my equation. Let's fill it in. First, we have to write 3 equations. So the equation they gave us is L of t equals AT squared plus BT plus C. So our first point, you don't actually use the calculator, you just plug in. Are y'all okay if I just use the first 3 points? Okay, I'm going to select these first 3 points. These are the ones I'm going to use. These 3 data points. I'm going to use those 3. So my first one, I'll plug in 0 years. With the life expectancy is 76.75 when the year is 0. Now, don't waste your time simplifying this. Just plug in the value and leave it as it is. You don't have to waste your time simplifying it. There's one equation. How many do I have to write? Not 2 this time. What does it say right there? 3. We're writing 3 this time. So there's my first point. My second, 77.38 equals A times 4 squared plus B times 4 plus C. Again, don't simplify. And when you substitute with parentheses. And finally, my third equation. 78.19 equals A to the 8th, A times 8 squared plus B times 8 plus C. That right there would be your answer to AI. So your first point comes, those are your 3 equations. Actually, you don't have to even label that part there. Let me just do it like that. Your first point comes just by plugging in values. That's how you get your first point. Questions over that? No? Okay. Second point comes from getting your equation over here. Again, we need 3 decimals. You need at least 3 decimals. So I'll copy that over. So my A is approximately negative 0.9 006 or 007? 007 when I round. Your B approximately is, I don't have much room here, 0.247 or 48? 47. And finally, C is approximately 76.662 or 663? 663. That would get your second point. Okay, last little part here for this page. It says, what year does the model predict the life expectancy of a child to return to 77 years? So what is 77 represented by, the X or the Y? The Y. The big key here is I would circle that up and make sure you have your variables correct. This means Y equals 77. That's not the answer, by the way. Some people, when I do that, think that's the answer. I'm not saying the answer is 77. That's what we type in the calculator. Type in Y equals 77. Say that again? Will I die when I'm 77 years old? Will I die? Will I die? I don't know. You don't know. Okay, it says, when will the life expectancy return to 77 years? Okay, look on this. If I zoom out one time, there are two possible answers. Which one would be returning to 77? Would it be the first one or the second one? The second. We don't need that first value. That's the one we want right there. That's where we're going to get our answer from. So it says, what year does it predict? Is the year 34, or basically year 35? Would that make sense to say year 35? No. This was years since when? 2004. So the year would be 2004 plus approximately 35 years. I'm going to round on years to the nearest year. So the year will equal 2004 plus 39 years. 35 years. I'm sorry, 35 years. So what year will that be? 2039. For people born in 2039, they're predicting that people born in 2039 would live 77 years again. Now, does that mean that's actually going to be true? No, this would, if you think about it, what this would say if you projected this out, that's people born way out some point in time in here. Let me get there. People born 125 years after 2004 would have a life expectancy of 0. Would that make sense? No, so at some point in time, this model is no longer any good, but that's how it works. Okay. Let's try part B. So now it says, coming back over here, use this given data. BI, it says use the given data to find the average rate of change in life expectancy from t equals 8 to t equals 19. So remember we had the t values earlier? When was t equaling 8? This was 0, 4. Okay, so from 2012 until here's 19. Okay, we want to find the average rate of change. We have a acronym for that. What's the acronym? AROC. How do you find AROC? It's change of y over change of x. Just make sure you plug them in correctly. What are my y values? The top numbers or the bottom numbers? You know what? I'm going to change this. What is y actually represented by and x represented by? Well, x is the years. So it's the change of t over the change of your life expectancy. I'll just do an L for life expectancy. Or you can do L of t if that makes you feel better. So my two time values are, what did they give us? We're using 8 and 19. We're using these two right there. So my two time values, you do this, the second minus the first. So it'd be the 19 minus 8. And in the numerator, it would be 78.87 minus 78.19. I don't want to mess that up. I'm just going to type that whole thing in the calculator. 78.87 minus 78.19 over 19 minus 8. I'm going to write this as a fraction, maybe? No, I won't. I'll just write it as a decimal because it says right here as a decimal approximation. How many decimals do we need in here? We need 3 decimals, so this answer would be 0.0618. The units here, this is years. Life expectancy would be total years divided by years. I'm just going to leave it like that. That's my answer right there. This would be worth a point right there. That's the answer to BI right there. Now, it says on part BII, is everybody tracking with how I got that? Any questions over that part? On BII, it now says, use this average rate of change to estimate the life expectancy of a child born in 2014. Now, here's my problem. Here's what students do wrong all the time. Here's what students do wrong. Y'all ready? It says use what? Here's where many of you might mess up, is you're just going to say, oh, wait, year is 10. I'll just go over here and I'll type in year 10. That's an X, sorry. X of 10 and get this number right there. And that's incorrect. That's not the number we want. It says use the average rate of change. So this is how much it's changing by. We're at year 8 right now. You see this point right here is year 8? Here's how you do this. You write an equation. You use the transformations that we just used last class. And it's this, that the AROC is the same thing as your slope. So you're going to do AROC. And then you're going to plug in your point where your X is a liar and your Y is a truth teller. Now you might be going, wait, where are these values? I'll explain it to you. Our estimate, I'll do Y hat here for estimate because I did that earlier. Our estimate is going to be on this problem, this AROC, 0.0618. That's actually 4 decimals. Times, now they gave us this value right here. This is our X. X is 10. I can put that in there. And now you plug in a point. I'm going to call this one X1, this X1, and I'm going to call this Y1. Is everybody seeing where I'm getting these values? The first point they gave us. So it would be X minus X1 because X is a liar. That's why I'm subtracting the 8. It's a liar. It says positive 8. I'm putting in negative 8. Plus the Y value, which is a truth teller, 78.19. I'm going to type that in the calculator and see what I get. So 0.618 times 10 minus 8. Again, you can simplify if you want. I'm not worried about that because I'm using the calculator. I'll type all that in. I'm getting 78.31. What should we get when we round that? 78.314. That would be your estimate here. 78.314. Now, I want to just contrast this. That's the actual value right there. That's the true value. Did the calculator predict the same answer? Please look. Did the calculator give you the same answer? No. That right there would be, if you went off the calculator, you would be wrong because this did not say use the model. It said use the average rate of change. An average rate of change comes from a line. It's like a slope of a line. Go ahead. Okay, so I just want to be really clear on that. Another way students have asked, can I do it this way? If I know it changes by this much, here's another way. Y'all ready? Starting at year 8, how many years does it take to get to year 10? 2. What you could do is you could start with this amount. So let me delete some of this here. I'm going to delete that and delete this. You could start with this amount here, 78.19. 78.19. If that's what it is in year 8, all you do is add the AROC twice. Why would I add it twice? Because AROC is how much it's changing on average. If this is year 8, you see how that's year 8? Adding it once gets me to year 9. Adding it again, guess what I get now? Thank you. I get the same exact value. See how that also worked? So if that's easier for you, do it that way. start with year 8 and then just add it however many times, the AROC, add the AROC, however many times you need to get to the year. Does that make sense? Okay. Last part. The average rate of change found in I can be used to estimate the life expectancy for children born in year 2004 plus T, while T is less or greater than 19. It says here, are these estimates found using the average rate of change less than or greater than the life expectancy for the model in AII during the year 2004 plus T when T is greater than 19? Okay, help me out. Is T an X or a Y? X. So go to your calculator, type in X is greater than 19. Did y'all type that in? The question is our AROC going to overestimate or underestimate compared to this model once X is greater than 19 over here? So let me see if you're understanding. AROC is what type of a estimate? Is it linear or is it quadratic? What was the AROC? AROC is linear. Is this slope positive or negative? Positive. So you have some positive slope right here. This model, after, you see how this is concave down? Let's see if you remember your rules. If this estimate is concave down, what does it mean about the AROC when X is greater than 19? Are the AROCs getting are they increasing or are they decreasing if you're concave down? Decreasing. So here, are the estimates found using the average rate of change less than or greater than? You would say the average rate of change, the estimates, I'm starting at this sentence. The estimates found using the average rate of change, rate of change is greater than the life expectancy predicted by model L. The reason is, since the model L is what? What did we say about the model L? Go ahead. So the reasons the estimate using the average rate of change found in BI and BII is greater than the life expectancy by model L. I just basically copied those sentences. By model L, I didn't put the when or for T greater than 19. Here's the since. Since this model is concave down, the average rate of change would be increasing or decreasing. If the graph is concave down, did the average rates of change increase or decrease? Decrease. So the reason this estimate right here, the one we're looking at, the one that's not changing, that one on the paper would be greater than the average rates of change after, because they would be decreasing on this interval. They keep decreasing because it's concave down. Make sense? Are you following what I'm saying? Are y'all putting this together, or you've forgotten this from earlier this year? If this is concave down, what would it mean about the average rates of change on a concave down? They keep getting smaller and smaller and smaller. This one's locked in from 8 to 19. This one's saying when T is greater than 19. So from 8 to 19, we have some average rate of change, but these, they keep decreasing. If you wanted to know what the average rate of change would look like, I could have typed in this equation right there to show you. Y equals 0.0618. X minus 8 plus 78.19. Sorry. That's what the average rate of changes look like. But if you keep making more and more average rates of change, they're going to get smaller and smaller and smaller because it's concave down. That kind of clicking with you? This average rate of change is greater because this one was concave down. All right. That was the longest problem ever. Yeah. Whew. Example 4.